1, 2, 3. All right, so let's see. Okay, looks like we are there. I just need someone to tell me if you are listen, if you hear me. Going to start soon. The light's not good here, but anyhow, so let's get this work. And if someone tells me, yeah, okay, thank you very much. So I got information that we are on, and I will start very shortly at 2100. All right, thank you very much for being here today. This is the last opportunity to answer some of the questions, and I'm going to be looking here on my right side to the chat and to see what questions are coming. But to give time, because there is always a little delay on YouTube, I'm going to address a question that was posted on Piazza, and then that's an opportunity to talk about that here so that everyone can hear the same explanation. So the question was about the previous exam, and it talks about the selene cysteine, and the question was, I was wondering why the protonation for SEC, which is the three-letter code of this amino acid, is at pH 9.5 and not 5.2. And the question is a little bit vague, but the example was drawing there. And I think that's a little bit of a confusion here, is because there is 3 pKa's for this amino acid, right? So there's the pKa 1 that was for the carboxylic group, that's the first one to deprotonate. And the second then would be the SEC that would be deprotonated. And then the side chain, and then finally the amino group. So that's what exactly what's there in the key for the exam, the answers. And the PI was calculated when we get the 0, then we divide, we sum the pKa before and the after and divide it by 2, and we got 3.85. Now, the question might be related to the next part, was question 2. But that question 2 is asking what pH is the alpha amino group in selenous cysteine 50% deprotonated. So this question is specifically for the third step, not the second step. It's not selenous cysteine. Selenous cysteine is going to deprotonate at 5.2. That's the pKa. The question here was for the side chain, the amino group. And for that reason, the answer for that question was 9.5, because that's when the 2 species are equal concentration. And it is specifically talking about protonate and deprotonate amino group of these amino acids. So that was the answer for this question. Another question that was asked also just after the office hour ended today, a student came and they asked this question, and another student asked the same question. Therefore, I thought I would start with that one first, before I look here at the chat and answer your questions, okay? Another question that just surfaced a few minutes ago on Piazza is that for question 15A and 15B, and this refers to one of the previous exams, okay? And what does model 1 refers to? Why is SCI the model 1 alpha helix and not S0? So this is a little bit of a misunderstanding here. It's because this is the first protein of the group that was found. And we're going to see that when we study hemoglobin, that everyone who has the priority, who does the first type of protein, they created the nomenclature that everyone has to follow, okay? So before we knew these structures of these proteins, we all thought that they transpass the membrane 7 times, beautifully embedded in the membrane 7 times, going back and up and down 7 times. Then, when the real structure of the protein was determined, the first one, and this is not many years ago, maybe how many years ago? A couple of years ago, it was the first structure was determined. Then at that point, the person who identified that structure, his name is Joel Butterwick. Joel looked at this structure and he found this helix, which would be the transmembrane one. He notes that it was broken. The helix was broken. Then he decides to call it S0 and S1 instead of TM1. So therefore, everyone follows that nomenclature. So do not go too far on that one, because always, whatever is the question about the structure, we always are going to give you hints that allows you to figure out exactly the segment that we are talking about, okay? Whether they call it S0, S1, we are going to tell the amino acid residue that we are talking about, and this is important for tomorrow, like I said in the office hour today as well. We need to count, and sometimes we give a hint about this, the length or how many amino acid residues are there by telling the first amino acid residue and the last one. And then we subtract the n and add 1, and then we have the number of amino acid residues, okay? So this type of important questions, and again, might be in the exam tomorrow because that's always the case, all right? So let's see here. I was wondering if you could briefly explanation how we find the PI of a peptide. It confuses me because I'm not sure which amino acid I focus on. Okay, that's a very good question. I would say that there will be no question about calculation of the peptide PI itself tomorrow, okay? I'm not going to ask any question. I just show in class an example how we calculate that. Remember, we put all the whoever is protonated and then calculate the net charge. For example, 3 plus. And then we deprotonate the first one and change that to 2 plus and things like that. And went step by step until we cross the 0 and go to -1, right? When we cross that line, then we know the pKa before and the pKa after. We calculate the average of these two, and they give us the PI. For now, I'm not interested in this calculation itself, but rather for you to understand when we have a predominance of certain types of amino acids, whether they are going to influence the PI to be high or to be low. And that's based on an example that we gave in class. We talk about insulin glargine, remember? And we talk about insulin glargine. What the industry did, it was they added 2 amino acid residues that are basic, arginine. There's 2 R's, additional 2 R's in that particular insulin. And with that, the goal was to increase the PI, okay? Because they wanted to take advantage of this in terms of aggregation of that particular protein. So they put it 2. And the example that I gave the other day, and I mentioned this in class today, in the office hour today as well, the example that I gave of the peptide on Valentine's Day, that peptide, if you look at it, you see in the office hours, that lots of acidic amino acid residues. So what they are going to do, if you don't have any residues that protonate or deprotonate, just the amino group and the carboxylic group, is going to be around 6, because these 2 are going to be, you calculate that's only 2, give around 6. However, if you start having amino acid residues that are like R or lysine, basic amino acid residues, then we are going to increase the PI. So we expect them to be above 7. If you have a lot of amino acid residues that are acidic, then we're going to come down the PI. And that was one example that I gave exactly for that reason. I want you to think about that, not to calculate exactly what's the exact number, okay? because that can be done in these days. I can put on like I show in class, you can put in a place that calculates this thing for us and give the exact number. We don't need to do all this calculation. But I want you to know the principle of this calculation. Okay, so let me try to answer the question here, otherwise the chat goes away and I don't see it. I was wondering if you could have, okay, I was wondering if you have to know how to do protein salting out and the hydrophobic interaction chromatography techniques for the midterm. Well, this was part of the midterm, so that will be a fair question if you are going to be there tomorrow. But of all techniques in chromatography, these are the ones that I emphasize the least. Okay, so having said that, the chances of being there tomorrow is very small. But the principle is very simple. We use a high concentration of salt, so we sequester water. We remove water availability to make these hydrogen bonds and so forth. So the protein ends up collapsing, and it loses the structures, and it then exposes the hydrophobic sites, and the hydrophobics then interact with each other. Or in case of just precipitating the protein because they cause so much interaction that they need water. Without water, they cannot make this hydrogen bond, make things soluble, expose something to the environment outside. So therefore, that's the principle of salting out. And you can salt out itself and put it there, precipitate and take the protein, or we can salt out in terms of using for hydrophobic interaction. We put salt so that it creates more hydrophobic interaction. Then when it finishes, you are going to start to decreasing this amount of salt so that we recompose the protein and get it then out of the column, okay? So that was a question. Can you briefly go over what is used to outcompete and what protein comes out of histag protein and the nickel column? Good question. Nickel column based on nickel interact with histidine, right? And the histidine has an imidazole group. Imidazole is also a chemical compound. We can have imidazole in the lab. So we make a solution of imidazole and we pass through the column. Now, because we have a higher amount of imidazole that we are put in the solution, compete with the same side of nickel, there is much less protein, they interact with the nickel, the imidazole that we had, and the imidazole from histidine is released because there are less amounts available, okay? So basically, it's a competition in terms of whoever has a large amount would win this competition, okay? Let me see the next one. Why do we have to use the quadratic form to find the x value? For Christ's sake, forget about quadratic form in my exams altogether. Not only tomorrow final exam, there will be never in my class questions that have a quadratic formula. Quadratic formula is important to know that we use that, but that takes a long time. Even if you use a calculator, it takes a long time to solve the problem, and they tell very little about your understanding of the material. So for that reason, I never ask in my exams question that will require the quadratic formula, okay? So without going too much into the specifics, so I would answer this question this way. Can you explain how to make identification in ribbons, such as where is alpha, helix, beta, and so on? Okay, so tomorrow is going to be more focused on alpha helix because I promised that the material for the exam would be the lecture before yesterday, right? And we stopped exactly in alpha helix. And yesterday we started again, and then we continue, and then we talk about the beta strands and how do they make hydrogen bonds and they form beta sheets and so forth, right? So there will be no beta strands in terms of evaluation tomorrow, but there should be alpha helix. How do we name them? And there's different, we are going to see when we study hemoglobin and the myoglobin, these people identify first, they call A, B, C, D, and everyone has to follow that nomenclature for them because they did that. For other proteins, we go by alpha 1, alpha 2, alpha 3. Most important thing is that whatever you do, you always start from N and then go to C. Okay. Now, in an exam, like I said in the office hour today, if you have some, we are going to always give some hints. And one of the hints is that the color of the helix, right? Because we know that comes from the blue to the red. If there is a red color there, and it's from blue to red, then you know that this is C terminus. If there's a blue color, you know that's going to be the N terminus. And if you say that's the alpha helix alpha 2, for example, then you see the blue one, and the next one is going to be alpha 2. Okay? So that's simple. Don't make a big deal of that now, okay? All right, so do we need to memorize which amino acid are acidic and basic, or just what basic raises PI? You need to know the properties of the amino acid, okay? So we have the two amino acids that are acidic, the aspartic acid and the glutamic acid. You need to know that there are two amino acids that are basic amino acids, such as lysine and the arginine. We need to know also this hydrophobic amino acid. They have like valine, isoleucine, leucine, and things like that. And we need to know what's the aromatic residue. So this basic principle you need to know, not only because of the exam tomorrow and the final exam later, but also because we're going to take 103 or we're going to take 104. And in either of this class, they are going to need all those properties of the amino acid. And they are going to take for granted. They are going to start from that, no review or nothing. It's based on understand that you already studied that, okay? So it's two different imidazole. I think that's this question is with related to the answer that I gave you before. Is that yes, that's an imidazole in the protein that's part of a histidine, that's the imidazole group there, and there's another imidazole that we are putting in the solution. So in the solution, I can put how much I want, so I can put a higher concentration. So that's a sheer competition. It's the same principle that you do for everything. If you have a column that you are using ion exchange chromatography, an ion exchange chromatography, you have a resin, you have a protein that's negatively charged, you have the protein bound to your column. Now I wanted to remove that protein. What do? I use chloride in high amount. So it's a competition, and whoever has a higher amount would win that, okay? Because they are bounded there, and there is another one that comes with a higher concentration. All right, how much of protein structure do you need to know, like keratin filaments, collagen, and animal hairs? I would say that you need to know for keratin, we didn't know all these details of the hierarchy of the formation, everything. We need to know that keratin, we need to know that the structure, the alpha helix that they have. You need to know that they have disulfide bridge that are very important. You need to know one or two things about the hair and how we break this disulfide bridge and how we reconstitute them and we make the sperm and the things like that. So this would be important to know. And for collagen, we need to know a lot of things about collagen. We need to know these alpha helixes that are forming there. And also we need to know that they have some very important post-translational modification, such as the formation of hydroxyproline and also hydroxylysine. So basically, when the ribosome make these proteins, they are going to make the amino acid, and we need an additional reaction to oxidize to make a hydroxyl group in this part of the protein, the proline in the lysine. How they make this thing? They use an enzyme. What's the name of this enzyme? 4-hydroxyprolinase. And they are going to make, basically, they are going to put this hydroxy group in an exact position in proline. And for that, this enzyme will need the help of ascorbic acid or vitamin C, because this enzyme has an iron 2, and when they do this reaction, the iron 2 becomes iron 3. And the enzyme has no other way to get it back to action unless vitamin C reduces this iron. So iron 2 is oxidized to iron 3. Iron 3 needs to be reduced to iron 2 to work in the enzyme. Okay, so that's the major role of vitamin C. So this kind of things you need to know very well. Okay, so how much protein extract? That was the question now. Could you demonstrate how to tell between, I don't know if this thing is not, maybe cannot move more than that, to tell between the right or left hand amino acid ribbons. Okay, so the thing is that you put it in the chest, your hand, right hand, and if you follow from N to C, going this way, clockwise in this case here, with your right hand you're going clockwise, then this is a right-handed. And if you have to use your left hand to go counterclockwise, then this is going to be a left hand helix. I will not worry too much about that for tomorrow, okay? But I think that's important to know, but for tomorrow specifically, I will not be so worried about that. Let's see if there is any other question here. Looks like that's all, unless I don't see. Yeah, I think that's what we have now. All right, so if you have still some more questions, just drop it there. If not, I don't want you to take too much of your time either. If you don't have questions, you have to memorize these amino acids, and there is no other way for that, right? So there's nothing we can do about that. I don't know if I just passed through some of the questions here that I didn't answer. Let me go back and see. No, I think I addressed all the questions that have been posted so far. I'll wait a couple of more minutes here, and if there are no more questions, then I will go take a rest. It's very important for you guys also that don't start until too late, okay? How can we know when a reaction has more than 2 pKa's in the equilibrium equation? That was a little bit unclear question to me, but I think that we're talking about amino acids with more than 2 pKa's. We are going to look at the table, right, and see what pKa's are there. The tables are going to be there. And like I said before, and I said in class yesterday, this time the data bank is going to be detachable. Okay, remove it, and please remove it, because you don't need that, and it's going to be problematic if you leave it there for us. So you keep it, you don't need it back. And there's going to be 2 sets of data there. There's going to be pKa for amino acids and the pKa for amino acid residue in peptides. So make sure that you use the right table if you need to use that, okay? So one is for pKa of amino acid, and another one for pKa when it's in a peptide. Amino acid by itself or when it's a peptide. And there's lots of information there also that you might need to answer some other questions, okay? I don't want you to give up too much information, but there are a lot of information there that we are going to find interesting and useful. So that's how we figure out, is basically looking at pKa's that are available. No one's going to give you a chemical reaction or something that's we don't know much, and we can't not. You have to know the profound details of organic chemistry to figure out whether there's more than 1 pKa. Okay, so don't worry too much about that. I think that's if I understood the question well, that's it. Do we need to use the Henderson-Hauser-Bag on this exam? And also, when it comes to cation exchange, is it named based? Okay, so these are 2 separate questions. First question is, do you need to know Henderson-Hauser-Bag equation? Yes, you need to know until the end of this quarter. You need to know Henderson-Hauser-Bag equation. Okay, I don't think that's going to be problems in the exam that's going to require a great deal of calculation. However, we need to know this equation because this is the principle. For example, the question that I just mentioned a minute ago about The question was about the pH of that 1/2 of the charges are deprotonated. That's based on the Hundert's-Rosenberg equation, right? The pH equal pKa plus log of the concentration of the conjugate base divided by the concentration of the acid. And because in that particular question was asking for when it's 50% dissociate, so that the two concentrations would be equal and the pH would be equal to the pKa. And the second part of your question was when it comes to cation exchange, is it named based on the protein that's kept in the longer or the solution? Everything in this business of chromatography, ion exchange chromatography, is based on the protein. If the protein is negative, you are going to exchange a negative protein by a negative ion. Okay, so we're going to make it. And if these two guys, either protein or ion, is going to be negative, so the resin has to be positive, correct? We're not going to have an interaction if they are not the opposite charge, right? So when I call anion exchange chromatography, it means that my protein is negatively charged. And I use an ion that's negative, which normally is chloride, okay? And in that case, the resin has to be positive. Now, if my protein is positively charged, I have to use a positively charged to exchange. Example that we gave in class, lithium, okay? Positive and positive. In that case, the resin has to be negatively charged, okay? So the name refers to the state of the protein, not of the resin. The resin is just the opposite of the what we get for the protein, okay? All right, so should you memorize the pKa for the 9 amino acid change from lactose to 6? For Christ's sake, don't do that. That's a waste of memory. This is going to be in the exam. Data bank is going to have exactly that information there. That's what we're going to give. We're going to give the N terminus and the C terminus pKa. Each amino acid is different, right? There are 20 amino acids. I'm not going to put a table of 20 amino acids there, which by one. So what I normally do, I take the average of the N for all amino acids and the average of carboxyl for all amino acids and put the average for this. For the side chain, I put specifically one by one, all of them. The same case for peptide. Peptide, we're going to have an N terminus. In the case of peptide, there is no need to average because peptide has only one N terminus, right? And one C terminus. And possibility of various amino acid residues there, 7 of them, right? In that case, they are all going to be there in the table. So there's no need to memorize for this exam or for your rest of your life. We don't need this. There are tables for that, okay? So let's keep the memory for other things that are more important. So I hope that it would clarify that. All right, so let's see. In efficiency experiment, does the order matter for the steps of dialysis and oxidation, and whether it becomes active or it ends up scramble the disulfide bridge? Yes, the examples of Atkinson is that in one example, he did not the dialysis. So let's say urea. What urea is doing there is to disrupting all the structure of the protein. So if the one step he didn't do the dialysis, he didn't take out the urea and oxidize, the cysteine went make disulfide bridge wherever they encounter each other. But it was not the right position. So the out of 105 possibilities, only one was correct. So therefore, he got 1% of activity. When he did dialysis first, he removed all this reagent. Now he oxidized, then boom, 100% activity. It means that now there is no other factor interrupting the proper folding of the protein. But if the urea remains there, urea is a disruptor. urea causes denaturing of the protein. So it could not get what he needed with urea present. So he had to undergo make dialysis first. Okay, so that's basically what it is for the amphincene experiments. That's a very good experiment that sometimes is interesting to ask questions about that. For protein salting out, since the salt will increase the hydrophobic interaction, that means that the protein that with the most hydrophobic interaction will elute out first, or is the opposite. So they all back over there, right? And now we are decreasing the salt concentration, okay? So if you start with high concentration, you start decrease. Normally in chromatography, we start with lower to high. For example, sodium chloride. You want an ion exchange chromatography, I go from so low to high. In desalting, we start with larger to low, okay? So the one with the highest interaction are going to be sitting there, and we are going to decrease the salt concentration, to remove it then step by step. I would not worry too much about, like I said before, about the hydrophobic interaction and salting out. The three techniques that are most important are affinity chromatography, gel filtration, and ion exchange chromatography. Okay, we will have to memorize the purpose of cyanogen bromide, or just trypsin, chymotrypsin, and endoproteinase lysine C. The former. We needed the four, we needed the three enzymes, and we needed the chemical process, which is the cyanogen bromide, when we needed to break the protein where there is a methionine there. Okay? All right. I think that's all. It's about half an hour that I wanted to talk to you, and see if you have any questions. I hope that's helpful, and hope that you have a good rest of the evening. And don't forget to memorize these 20 amino acids, and be ready for tomorrow. Questions that are normal for this type of exam is that you have a peptide, you have to name it. Tomorrow, if your peptide doesn't make any meaning, like for example, we have a peptide today, we said Ash Wednesday. It read nicely, but tomorrow if you have a peptide and doesn't make any sense, it's not the Walter or it's not the Gary May or something like that, don't worry about that, okay? Just look at that, trust your feeling that you know the amino acid residue, make sure that you mark the N-terminus, the C-terminus properly, and then we go from there. And then when we have that thing, whatever the next question is going to be, go from there. The question might be, use one of these enzymes to chop off your peptide. Or maybe what's about the PI of this peptide? Things like that. It's very common. I mean, it's no secret, okay? And also, there will be questions. Group 1 is going to have one exam. Group 2 a different exam. And they're going to ask, write the amino acid A, B, C, D. The other one is going to write the amino acid F, G, H, I. Something like that, okay? So, you have to memorize these amino acids because you need to write. How do you write? I don't care. You can write in like lines, or you can write a C. As long as you show that you know what the amino acid is, that's important for us, okay? So do not worry about it. How do you draw the amino acid residue? We need to know also the amino acid when there is this titration process of amino acid, right? We need amino acid that's protonated, and we deprotonate at the various steps, and they go down there. And this kind of things you need to know, and you need to interpret those steps and be able to assign them, okay? I think that's all for now. I wish you very well in the exam tomorrow, and I look forward to see you there. Good night.